communicate using registers. Okay, so what's consensus? In consensus, every process PI has an input value xi, and if it doesn't crash, it has to output a value of yi, such that the following two properties hold. First, validity, that each output yi is one of the inputs xi, or x1 through xn, and moreover, there's agreement that all the output values are the same. Okay, so consensus is another word for agreement. Okay, and wait-free means that every process terminates within a finite number of steps, no matter what the speed of the processes is, and even if other processes crash. Okay, so the theorem says that there's no wait-free algorithm to solve consensus among two or more processes in an asynchronous system where processes communicate using registers, namely they read or write. The proof of this theorem uses a valency argument, which is a technique that was first introduced by Fisher, Lynch, and Patterson to prove the impossibility of consensus in an asynchronous message passing system. So given an algorithm that claims to solve consensus, one first proves that it has an initial configuration that is bivalent. This means that there is an execution from the configuration in which some process outputs 0, and another execution from this configuration in which some process outputs 1. In this diagram, a node represents this little figure here. Okay, a node represents a configuration, and an edge represents a step by some process taking the system from one configuration to another. I'm going to use a purple node to denote a bivalent configuration. Okay, oh, yeah, okay. So we have an initial configuration that's bivalent. Then one shows that for every bivalent configuration, there's a step by some process that results in another bivalent configuration. This implies that the algorithm has an infinite execution, and hence the algorithm is not wait-free. That's a very easy result, a very easy proof. The details that I haven't told you aren't very difficult. K-set agreement is a generalization of consensus. It allows k different values to be output instead of 1. And in particular, when k is equal to 1, K-set agreement is the same as consensus. So again, every process has an input value xi, and if it doesn't crash, it has to output a value yi. The same validity property, each yi has to be one of the inputs, and the agreement properties that most k different values are output. Now, it's also known that there's no wait-free algorithm for solving K-set agreement in an asynchronous shared memory system where processes communicate using registers. The proofs of this result are considerably more complicated and use arguments from combinatorial topology. A natural question is whether there are simpler proofs of this result.
Wait, can I ask you, can you back up one more? So sorry, just to make sure I understand this. So all the k values have to be legal?
Yeah, so by validity, what we're saying is that all of the outputs have to be one of the input values. And we were saying that a total of k different values can be output. So if we're talking about two-set agreement, then there can be most two different values.
This is not randomized?
No, we're not talking about randomized algorithms here. No, this is all deterministic. Unless I say otherwise, no, I'm not going to talk about anything randomized here at all. Yes, you can actually, there are solutions that are randomized, but we're not going to talk about that. Okay. Anyhow, all right, so we have this these very complicated proofs using combinatorial topology, and some of the authors here got the Gödel Prize for proving this result. So it's, there's some meat here.
All of these works were independent.
Yes, they were independent. They all appeared at the same stock conference. Yeah, it was weird. That is true. There were 3 different groups, and they were slightly different proofs. The proofs weren't all exactly the same, but yeah, they were all using some form of combinatorial topology. Okay, so just before the pandemic, together with one of my grad students, a postdoc, and a couple of colleagues, I formalized this question by defining a class of extension-based proofs, which includes valency arguments. Then we proved that there's no extension-based proofs proof of the impossibility of k-set agreement when k is at least 2 and n is greater than k. Okay, so why am I talking about extension-based proofs at this workshop? Okay, so this result is related to results in proof complexity. This showed that certain theorems cannot be obtained in weak formal systems. For example, Toni, Paul, and Russell proved that there's no proof of the pigeonhole principle using relativized bounded arithmetic. And in the early stages of our research on extension-based proofs, talking with Toni about what we were doing was very helpful. Okay.
What is relativized?
Maybe you should ask.
So you add like a relation symbol,
Sorry?
and you add a relation symbol, and you're allowed to use it freely, like in induction. So that relation symbol would be like the Pij.
But this result is the same as the AC0 Krega lower bound. It's just a different way of viewing it.
It really doesn't have a whole lot to do, except for sort of the
Yeah.
motivation. It doesn't have a lot to, you don't need to know about that for this talk.
There is, when you say there is no proof, there is no short proof. Or,
No, at all.
Well, no,
No proof at all.
Yeah,
In-
so
in
that,
the-
I mean, so that's really what we've shown here, is that there's no proof in this extension-based proof, which is a restricted kind of proof family that can be used to prove this theorem that we know is true.
I think if there was a proof, correspond to short proofs or any particular.
It's short proof, it's not the, oh,
Complexity.
okay, the proof complexity such, okay, fine.
Yeah.
All right, so let me tell you about extension-based proofs and some interesting things that we've been able to show about it. Okay, so an extension-based proof is a game between a prover and an algorithm, which the prover is trying to show is incorrect. The prover repeatedly asks queries, and the algorithm responds to them. The prover's queries can be chosen adaptively based on the responses it gets from the algorithm. Now, initially, the prover has only reached the initial configurations of the algorithm. The prover may ask a single-step query by choosing a configuration C it's reached and a process P that hasn't terminated in C, so that's still active. And the algorithm responds with what happens when P takes one step starting from C. It describes the resulting configuration C prime. In particular, it gives a new value of the object that P accessed, P's new state, whether P halts, and if so, what output P output, what value P outputs. The prover wins by showing that the algorithm is incorrect. So one way the prover wins is if the algorithm responds with a configuration in which the outputs violate the specification of the problem. For example, if the problem is two-set agreement, the prover wins if more than two different values were output in configuration C prime, violating the agreement property. So over here. Okay. The prover also wins if some process outputs a value in configuration C double prime, but C double prime was reached from an initial configuration in which no process had that value as its input, violating validity. Okay, so if here the input values were 0, 2, and 3, and all of them output 1, they're agreeing, but they're agreeing on an invalid value. So this would be incorrect. A chain of queries is a consecutive sequence of single-step queries, where the resulting configuration of one query is the input configuration to the next query in the sequence. A second way the prover can win is if the algorithm allows the prover to continue a chain of queries indefinitely. This shows that the algorithm violates white freedom. Now, extension proofs have one more type of query, which is called an output query. For an output query, the prover chooses a configuration C that is reached, a set of processes Q, and a possible output value Y. So we have that triple CQY. Okay, the algorithm can respond with a finite sequence of steps by processes in Q, such that starting from C, one of them outputs the value Y. Alternatively, it can say that no such sequence exists. For example, if Q is the set of all processes, then the output query CQ0 asks whether there's an execution starting from C in which the value 0 is output. Likewise, the output query CQ1 asks whether there's an execution starting from C in which the value 1 is output. These two queries tell the prover whether the configuration C is bivalent, okay, because there's two different, an execution outputting 0 and an execution outputting 1 if it gets a positive answer to both. After making finitely many output queries and chains of queries without winning, the prover must choose a configuration C it first reached during this phase, and then it starts the next phase. This phase is the same, except that the prover can only ask queries about the configuration that are reachable from this new configuration C. This keeps on happening until the prover cannot start a new phase, because all the processes of output values and terminated in the configuration it chose. In this case, the prover loses because it hasn't shown that the algorithm is incorrect. If the prover asks an infinite chain of queries, or there are an infinite number of phases, the prover has demonstrated that the algorithm is not weight-free. Now note that a valency argument is an example of an extension-based proof. Okay, so what we did, besides giving a definition of an extension-based proof, is we proved that there is no extension-based proof of the impossibility of a weight-free algorithm to solve k-set agreement for k greater than or equal to 2 processes, for k greater than or equal to 2 among more than n processes. Our approach was to adaptively construct an adversarial algorithm that wins against every prover. Okay, so it's sort of a flip of our normal adversary arguments. We later showed a similar result for a different problem. Specifically, we proved that there's no extension-based proof of the impossibility of a weight-free algorithm to solve approximate agreement among more than 2 processes on a cycle of length 4 in an asynchronous system. Okay, so what's that problem? Well, let me talk more generally about approximate agreement on a graph. Okay, so here we have graph G with vertex set V and edge set E, and each process has an input xi, which is a vertex. And if it doesn't crash, must output a vertex of G, satisfying the following 2 properties. First, every output vertex lies on the shortest path between 2 input vertices. In some sense, you can sort of think of this as being somewhere in the convex hull of the set of input vertices. Okay. Secondly, the set of outputs are within distance 1 of one another, so that the set of outputs form a clique in G. For example, if x1 and x2 are 2 inputs, the inputs of 2 processes, then y1 and y2 are allowable, is a possibility for their outputs. Okay, and so on a cycle of length 4, essentially our graph is just a cycle of length 4, a pretty trivial one. And even there we can't solve approximate agreement. Seems like a very, very simple problem. Okay, recently a more general result was obtained by Shihao Liu, who is my graduate student. He showed that there is no extension-based proof of the impossibility of a weight-free algorithm to solve approximate agreement among n greater than more than 2 processes on any connected graph in an asynchronous system. All right, so let me change. Let's talk about another aspect of this. So everybody here is familiar with reductions, and reductions are used throughout theoretical computer science to transform impossibility results from one problem to another. Specifically, if some problem T reduces to another problem S, and T is impossible to solve, and so is S. A natural question to ask is whether reduction can be used to transform an extension-based proof from one problem to another. Specifically, if problem T reduces to problem S, and there is an extension-based proof that T is impossible to solve, is there necessarily an extension-based proof that S is impossible to solve? Although I don't know the answer to this question, I do know something that's pretty close. Together with one of my grad students, I defined a larger class of proofs, which we called augmented extension-based proofs. And we showed that many reductions can be used to transform an augmented extension-based proof from one problem to another. We consider reductions from problem T to problem S, which involve solving only one instance of S, but allow processes to communicate with one another beforehand and afterwards. Formally, each process PI is given an input XI. The processes first solve problem R1 using a known weight-free algorithm. Then they solve an instance of S, where each process's input to S is its output from R1. Finally, they solve problem R2 to determine their outputs using a known weight-free algorithm, where each process's input to R2 is its output from S. These reductions are more general than many one reductions, but less general than Turing reductions. An augmented extension-based proof is like an extension-based proof, except that the prover can ask assignment queries instead of output queries. For an assignment query, the prover chooses a configuration C that is reached, a set of processes Q, and assignment F output values to a subset Q prime of these processes. Okay, so in particular, so we might say, okay, F Q1 is going to output F of Q1, Q2 is going to output F of Q2. And the algorithm can respond with a finite sequence of steps by processes in Q such that starting from C, it reaches a configuration C prime in which every process Qi and Q prime outputs the value F of Qi. So what it's assigned to do. Alternatively, it can say that no such sequence exists. An output query can be simulated by a finite set of assignment queries. Instead of asking whether there's a finite sequence of steps by processes in Q starting from C, in which one of them outputs the value of Y, the prover can ask for each process in P whether there's a finite sequence of steps by processes Q starting from C, in which process P outputs value Y. And so you can just do that for all processes P in this set. Okay. So thus, augmented extension-based proofs are at least as powerful as extension-based proofs. Okay, so we use the same technique to show the impossibility of k-set agreement has no augmented extension-based proof. Okay. Well, what does our okay? So we were also able to prove that if R2 composed with S composed with R1 is a reduction from problem T to problem S, and there's an augmented extension-based proof that T is impossible to solve, then there's augmented extension-based proof that S is impossible to solve. Well, what do we know? What does this our reduction theorem tell us? Well, there are known reductions from a bunch of other problems, such as k-leader election and k-test and set to k-set agreement. Since there's no augmented extension-based proof that k-set agreement is impossible to solve, it follows from the contrapositive of our reduction theorem that there are no augmented extension-based proofs that k-leader election and k-test and set are impossible to solve. Okay, now the last result I wanted to mention is that there are in theory of distributed computing, we're also interested in anonymous algorithms. And an algorithm is anonymous if all processes with the same input value behave the same way. In other words, what they do does not depend on their identities or their identifiers. Now, it's known that there are no anonymous weight-free algorithms for solving weak symmetry breaking or 2n-2 renaming among n greater than or equal to 2 processes in asynchronous shared memory systems where processes communicate using registers. And the proof of these two results also use combinatorial topology. Okay, another question that was posed in the original paper about extension-based proofs is whether these results have extension-based proofs. And it's straightforward to extend our reduction theorem to anonymous algorithms. If there's an anonymous reduction from problem T to problem S, and there's an augmented extension-based proof that T is impossible to solve anonymously, then there's an augmented extension-based proof that S is impossible to solve anonymously. Moreover, our proof that there is no augmented extension-based proof that k-set agreement is impossible to solve can be easily extended to show that k-set agreement is impossible to solve anonymously. Okay, since there are anonymous reductions from weak symmetry breaking and 2n-2 renaming to n-1 set agreement, it follows that there are no augmented extension-based proofs, and hence no extension-based proofs of the impossibility of solving weak symmetry breaking and 2n-2 renaming anonymously. Okay, so I just want to end here and say happy birthday, Toni.
Questions, comments?
Yeah, so in Modern arithmetic, you show that something cannot be proved, and this means that it just falls. So there's some model where it doesn't hold. So here you might say maybe there's some semantics where these impossible tasks can actually be solved. Like maybe you run the algorithm indefinitely and you choose some value that occurs infinitely often, or one of these things. Have you thought in this direction?
So, I mean, for the requirement that you have both validity agreement and wait for termination are necessary for all of in order to get the impossibility proof. So if you get rid of any of them, the problem is there's no problem. Okay, so in fact, I mean, if you get rid of validity, then everybody can just always output one and never worry about it. If you don't worry about agreement, everybody decides their own input. And with weight freedom, well, you know, if you manage to get an answer, fine, but if not, but there are randomized algorithms for solving this, for solving things like case-set agreements. So yes, so I'm not really sure what directions we can take this, but really what we're trying to say is that we would really love to have easy proof techniques to show the impossibility of these results. And it's just not possible. So people really have to get down and look at the combinatorial topology to be able to do that. So for example, to show that you have a cycle of length, it is actually impossible to show that there's no approximate agreement algorithm for a cycle of length 4. But then you have to use Sperner's lemma and a variety of other things in order to do that. And you can't get a lovely simple proof of that, a very elementary one.
Can you hear me? So this is a related question. So a lot of people here have been thinking and talking about these different TFNP classes, and one of which corresponds to Sperner. So I was wondering if you thought maybe in the other direction, that if you added, is there like was one of these like complete in the sense that if you added like Sperner or set agreement, this is a vague question, but if you added that to your extension-based model, then would you be able to prove all of these other ones that you're talking about?
I'm thinking, the model was very much like a communication complexity model.
Like a decision tree kind of model.
Yeah.
Right.
So
So like you had a notion of a reduction to an S. So let's stick with that same notion. Like, could you show that if you could reduce to some distributed version of Sperner or set agreement, that then, so you can still make this decision tree that you described, but now you can add S, where S is one of these problems. Could then you show that then you can solve the other ones? Or
okay, I don't know. I'm
does that
not
make
really
sense?
sure.
I know it's a little bit vague. But
Yeah, no. That sounds like a really interesting direction to go. I haven't thought about that, but.
What else?
Oh, I was about to ask something related to Tony's question. So, like, can you define some search problem related to refuting this algorithms and show like it's PPAD complete or some kind of that?
It's not quite PPAD because it's like infinite or. Anyways, it seems to be not. There's like it's infinite. It's not. I don't know how to make it fine. Anyways, I should let Faith answer.
I don't know. Yeah, there are some infinite issues.
I'm not really sure. I mean,
Like,
I guess the study of complexity classes within theory of distributed computing has been somewhat limited. And
yeah, I don't know. Maybe there is some financial version, financial formulation of this, and like if you show it's PPAD complete, then it means you really need to use this Sperner lemma to prove like the impossibility results.
I didn't even like, I was just gonna say like maybe a comment, like a lot of these lower bounds, like in complexity come from playing adversary arguments on like infinite models, right? Like there is no finite model, therefore we should be playing on the infinite model. So maybe that's the relationship between these things.
This is also related to the same issue. Have people looked at whether there's any formal connection between extension-based proofs and constant depth Frege proofs, for instance?
no,
Because it seems like it's possible there is, just because you have finitely many options at each stage and finitely rounds and so forth.
but I'd be happy to talk to people if anybody is interested.
And if there is, that would also give a formal connection back to bounded arithmetic and the pigeonhole principle you mentioned at the
Yeah,
beginning.
That would be really cool.
I have a comment, not my own, but seems relevant. So I remember Charlie Rakoff saying once something like, we think of lower bounds as reasons why algorithms are impossible, but there are many algorithms whose only purpose in life is to prove that lower bounds are impossible.
Right.
And I think you've given one.
Yeah, well, it's actually, the adversarial algorithm is not truly an algorithm. It only works on the part of the input that you're restricting yourself to. So it actually is not a real algorithm, but it only looks that way as far as the prover is concerned. So yes, it is definitely in that, it has that flavor to it for sure.
More questions, comments, solutions to problems? I see a paper being created.
That would be
From the
cool.
forums. Okay, thank you so much. That was exciting.